So, during the second half of the second part, Avi Mendelson will summarize and will lead the discussion. He is adjunct professor of computer science in the computer science and electrical engineering departments at Technion in Israel, and he also works at Microsoft R&D Center in Israel. Prior to Microsoft, he was with Intel for 10 years as a senior researcher and principal engineer in the computer architecture group. And there at Intel, he was the chief architect of the CMP feature of the first dual-core processor of Intel. And thus he is widely recognized as one of the key people to have started the CMP revolution in Intel and more generally. Before that, the first half of the second part, Sean Hale will present to us about the top-down approach. He is a fearless entrepreneur from Silicon Valley. He founded a fabless chip company in 1997 around a MIMD-SIMD low-power, massively parallel processor for graphics. Then worked his way up the software engineering food chain, ending up as chief software architect at Nevic. In the meanwhile, he has taught courses and seminars on object-oriented programming at DEC, SRI, Sun JavaSoft, etc.
Thanks. Okay, there's a lot to cover, so I'm just going to get right to it. First thing is, when I found out that... Can you hear me? No? You can hear me, nobody else can? Does this one work in the room? No? Okay. Okay. Yeah, I need speakers. I think it's a good idea. So maybe the speakers can come online partway through. So when I first heard that Yale was the other, I was kind of Yale is he's famous, and he's known all over the world. Been invited to all the different places to talk, and I want to give him all the respect. And I think part of the reason why I'm on the panel is because of the work that we're doing together with Albert Cohen and the Alchemy Group on parallelism, and some of my industry past, having been a project manager in software and hiring people and et cetera. And this change to parallelism it's a profound change. It very likely is the greatest change in the industry since the industry started. It works its way into every aspect of how we think about computers, how we program, how we design, and it's more than just an extra topic in a course. So things that have worked well in the past are unlikely to work well after this change, and we're going to need new approaches to teaching architecture and programming. And so this discussion, obviously we're in the midst of this change right now, so these are not final answers. This is food for thought. This is a starting point for a discussion. And I'm hoping that Yale will jump on board and help us with the next generation of students. So when teaching and in any other thing, we often get sub-goals, and we get focused on parts that are fairly far down the food chain. And so when things change drastically, a lot of the intermediate decisions that have been made that we're no longer looking at, they've gotten wiped out. So we need to go back and look at what are the fundamental goals that we're after in teaching, and use those as our guideposts when we're deciding in a particular course how we're going to design it, which decisions to make on how to do things. And so the goals that I'm proposing are to prepare students for work in the field. And what's important here is that you get students from a wide variety of backgrounds, especially freshmen. They've come from a variety of different schools and some with AP courses, etc. They'll come on when they come on? Okay. So first goal is to prepare students for work in the field. I did some numbers, and it turns out that it's around 5% of the students actually go on to graduate school. So if we're trying to maximize the benefit to the students, right, take each individual student, find the benefit to that student of being in this class, sum over all of them, that's the thing we want to maximize. And it's important for the students to enjoy the process. It's important for the students, there we go. It's important for the students to enjoy the process because learning itself, it's recursive, right? If they enjoy the process of learning, then they're going to be better at learning, and it builds on itself. And, you know, we love our field. We love computers. We love architecture and programming. So one of the goals is to get the students interested in joining this field. Get the good students coming into computers. So this is more of a sort of a comical break. There are many different observed goals in real professors, and these won't be references for the talk, but I'm going to skip these. So takeaway on the goals. You know, it's important to have those goals in mind, and here are a few numbers on the jobs. So this is done a survey on the web of job sites, and about 30% of the jobs are web, 30% are Java, 30% are C and C++. And I appreciate the remark about the languages are changing, but we don't know what the future languages are going to be. So we have to kind of anticipate and do our best. And the best predictor of future is the past. So the world is changing. Quick timeline so we can figure out where we've been and where we're going to. So ENIAC was the first. And you'll notice on this list, ENIAC, mainframes, desktops, current. It's been sequential all the way through. The main programming has been sequential. Just a small, tiny fraction of people have been doing parallel programming, and it's been notoriously difficult. So in ENIAC, it's machine code programming, mainly research people. You know, it's all about registers, it's all about performance. Mainframes, there's a little bit of diversity. You've got the business people doing COBOL. They don't care so much about performance. You got scientific people doing Fortran, and you've got systems people doing assembly. Corporate, very strict design process. And then you've got desktops, and the diversity increases again. We get embedded, we get all these different development processes, we get open source, things become informal, we get extreme programming and rational process and rapid prototyping, but we still have a single hardware image, right? It's x86, essentially. And the software developers get to write their software once, and they know when they've written the software, it's going to run. You know, they might have to tweak for the OS a little bit, but it's not a major change to switch. Well, they don't like it, but it's not as big a change to switch between operating systems as it is to switch between different kinds of parallel hardware. And so now, we've got this case where a lot of the performance is inside the tools. And we have a lot of the areas where programming takes place where performance is less important and productivity is more important. And the parallel programming that we're doing, it's threads and it's in flux. We're not quite sure exactly what the future programming process is going to be, but we can look at fundamentals, and there are a few things that we can figure out. So in the future, I expect that with performance portable parallelism, right? The most important thing here on this graph to take away is that in the past, this incredible success, and when you look at history of IBM and of Intel, it's been proven, it's been shown again and again, dominance of Microsoft, etc. That if you can write a program once, and you know that it's going to run on all the places that you care about, that's an economic driver that it's very difficult to argue with that. That's the dominating theme here. And so with the explosion in hardware, if you've got a cell processor, you've got GPUs, you've got Larrabee coming on, you've got these 100-core chips, Tylera's shipping 100-core chips now, you've got embedded, you've got all these different explorations in parallel architecture, and you still want your one program to run reasonably on all that different hardware. So if you put things into your code that this part of I'm doing in the code is for this particular hardware, then you lose that simple fact that your one program is decent on all of them because it's been done carefully for this one platform. So in the future, our applications are going to be blind to the hardware. And there are a lot of good reasons for that we'll see later. So parallel architectures will continue this explosion. Once you've got the paradigm where you can write the software once and you don't care about the hardware, then your instruction set opens up. You can change your instruction set at will. You're playing around with networks and hardware and message systems, etc., gets opened up, and startups are going to take off, and we'll see just an explosion. So the tools are the thing that are going to become much more key. In the past, tools, they're kind of this niche thing. Yeah, you've got your compiler. But in the future, tools are going to be our crutch. They're going to be as important as any other aspect of computer science. They're going to be on par with the hardware itself, is the tools that go from this single program to each of the different hardware architectures. So the takeaways from that, some of the things that will still be visible, number of operations is going to be visible. The number of memory accesses is going to be visible. And the use of references or pointers are still going to be visible in your software, especially for the portion that are doing C and C++. For parallelism, the things that will be important are dependencies, transform properties of the code, and the scheduling process. We'll see more about scheduling in just a second. So I actually didn't get hardware versus software, which maybe during the discussion, if anybody knows the breakdown. So we can kind of tell in this introduction to architecture and programming what percentage we expect of those students are going to go on to the hardware side and which onto the software side. So you'll notice this is an important theme, that one of the tracks is applications, one of the tracks is hardware, and one of the tracks is tools. And so that triumvirate is, I'm going to propose as the organizing principle for the class and for all the classes that follow on after. So the learning process, and I appreciate Yale's slides. I think we have a lot of agreement on people learn in terms of what they already know. So it's very important what they learn first, primitives. If we're assuming that the students come without one particular background, and this is the introduction course, so we are providing the view of the world for them. It's important that the first things that they learn in this class are ones that they can learn everything else in terms of. And I think for hardware, I think the light switch is absolutely the right way to go if you're talking about learning the hardware chain. So a couple of people, just some simple quotes. Some very two esteemed people who I believe are in the room. They were confused. They had learned registers, they'd learned assembly programming, and these are very smart people. But when they got to higher level languages, that transition, it just didn't make any sense. I mean, how is lambda in terms of registers, right? You're doing Lisp. So I'm actually proposing different primitives than register to register memory machine. So here's what I'm proposing. And I'm going to do an iteration on this, go through it a couple times before especially the software primitives start to make sense. So this set of primitives I'm proposing is the nexus of this triumvirate, right? All three tracks, the tools, the architecture, and the applications all meet at one set of common primitives. And there's a small amount of memorization. You know, we're basically pointing at these and saying, you know, this is the starting point, and we'll just let them learn by example on these and relate everything in terms of them. So the machine primitives are memories, and the processor has no registers in this primitive. It's just memory to memory. Everything is in memory and it goes back to memory. It's got arithmetic operations, it's got control operations, communication. We're assuming that parallelism comes from the start. The future is about parallelism. So in this world, communication is modeled as between memories. And the concept of animator is a very, very, very important one. This is a key concept. And so if you take a chip and you put it in your hand, what does that chip do? Nothing. It sits there. It's just a bunch of arrangement of atoms, right? It's exactly the same as a piece of software. You have to hook it up to electricity in order to animate it. And so it's the electricity, it's basically all the way down to quantum mechanics, but we don't have to go that far, that causes it to go. And if you're looking at the hardware, an easy way to think about what's animating the processor is the clock, right? It's got a clock in it, and the clock is run by the electricity. And the clock is the thing that makes the processor go from one instruction to the next instruction to the next instruction. So that's the thing that makes it run. And it's actually kind of surprising. Some of the freshmen who don't have much of a computer background, they're really confused about, you know, how does this program thing actually do something? And the animator concept helps with that. But it ties in, even more importantly, to the software primitives. So just briefly, for parallelism, the primitives are a graph, a machine graph. So you've got your communication between memories, and you've got your physical processor talking to memory. So you've got a graph of that, and that's how you represent parallelism in hardware in this primitive model. So now the software primitives. Here's where things start to depart a little bit. So I'm proposing the concept of a processor specification. So just like that chip in your hand doesn't do anything until the power is hooked up, any function in C can be put in hardware, right? We're doing reconfigurable computing these days. So there is no difference between a function in a language and a piece of hardware, an actual silicon arrangement of transistors, right? You can write a program on a page, and that's representation in little scratches, or you can write a program in little arrangements of atoms on a chip. They're the same thing. So I'm recommending a processor specification is what the code is. And then a software processor is a piece of code. I'll go on this on the next slide, actually, and show you a little bit more what I'm talking about. That piece of code has state, and it gets animated. So creating a software processor is created from a processor specification. For those who know object-oriented programming, a class is the processor specification, and an instance of that class is the software processor. So the thing that distinguishes a software processor from the specification, one of them, is state, and the other thing is that it has a scheduling process. So just like the clock is the animator for a physical processor, the scheduling process is the animator for a software processor. And the other elements are dependencies, are a primitive that will be seen throughout, and I'll show later how that works its way into all the aspects, all three branches. Transform properties are memorized results of looking at dependencies, right? You can look at a plus operation, and you know it's got the commutative property. Well, the commutative property is just remembering that when we went through all the details of adding, there were no dependencies that stopped us from switching the order. And scheduling constraints are key. Those are the things that stop the scheduling process from doing things. Those limit the scheduling process's choice. So in a sequential program, the language is designed with constraints implied by the primitives of the language, such that there's one and only one operation that can be legally scheduled at any point in the evolution of the state of a software processor from that language. And I'm going to show that in just a second. So a work unit is the unit of scheduling. You've got a software processor, you give it some data, right? You give it some parameters, and it goes and consumes those parameters and completes a unit of work. And then you've got the language primitives, standard stuff, recommending the arithmetic and control operations are seen as language primitives, references, data structures, dependencies, and scheduling constraints. And then you've got the semantics that are implied by the language. You've got the semantics of the language imply scheduling constraints. There's a scheduling process that is implied as being inside the language, which is the thing that is animating the primitives of the language, the keywords, etc., that make it go. And then state evolution, right? So you've got the software processor, its state changes. And I'm going to go to the next slide because I illustrate that here. So here we have some function. And this function is a processor specification. Right? That's what a function is. It specifies a processor. And that function is we're going to create a software processor from it. And that software processor is going to have local state. So the I and the J are local state inside that software processor. So when we create it, we create that local state for it, right? Software processor has that I and J, its own I and J as local state. And then the language primitives are going to animate that software processor, and we're going to see the state evolve. So here we can see the I gets the 1, and the J gets 1 through 5, and the I changes, etc. So the state evolution is in terms of the language, not in terms of the hardware. And this is one of the places where there's a departure between the sequential world and the parallel world. And this is an important concept for parallelism because the language, one doesn't know what the hardware is going to do in the parallel world. And so having this concept that this language, we create a software processor that is animated by this language and not by hardware, makes it an easier transition to get the concept that later, you have 10 different versions of hardware that animate they animate the same way that the language does in 10 different ways. So the animator has its own state, and we'll see in the second version of this how the compiler handles that. Okay, so the last thing I want to show on this slide is when the scheduling process of the software processor created from this specification gets to the point that some other function is the next thing to be scheduled, it actually creates a brand new software processor according to the some other function specification. And I'll show in a little bit on the hardware how that happens. I want to talk about these things, and the point is to iterate through these a couple times. And that's actually my recommendation for the class, is to iterate through these things. And at the point where some other function is called, software processor is created, local state, whatever local state it has, is created. It's got its own scheduling process that animates that software processor, and it's given whatever the current values of A, B, I, and J are in the point in the state evolution where it's called, right? So in between each of these I's and J's, that some other, in between each of the J's, that some other function gets called. So software processors are created each time, and that software processor is given whatever the current I and J's are. And that's scheduling. So the last thing I want to illustrate is changing the state evolution. And here's where the world of parallelism shows its face. So this is probably the most important thing as far as parallelism goes, is state evolution. So what the tools are going to actually do is they're going to make changes in the software like this one, changing the I and the J. Notice in the code? And all of a sudden the state evolution has changed. And now if we take that state evolution and we map it onto hardware, we're going to see how that affects the details of the hardware. And the job of the tools is to try all the valid transforms that it can, such that the new state evolution has better behavior when it's mapped onto the hardware. And I'll go into that a little bit more later. So the proposed course structure: 3 tracks, applications, architecture, tools. Iterate through them, give some cross-cutting concepts before each iteration to prepare. All 3 are anchored at the primitives. So the applications I'm recommending outside in, which is sort of top-down. Start at the top, which is the real world, and go to use cases, and then go down to abstract data types and patterns and algorithms, and then go down to language primitives. And at the same time, start at the hardware primitives and work up and show how the language is implemented in terms of those. The architecture, I'm recommending sort of the same process. Except this time, the hardware primitives are at the top, And I guess light switches would be the right place to start at the bottom. And then the third track, show state evolution mapped onto the hardware. How the structure of those processor specifications, right, the functions, relate to the manipulations the tools do, and see how the evolution of that state behaves on the hardware itself. And that, when programming, becoming aware of the fact that the functional structure of your program and the dependencies in your program are going to affect the tools, and know what the tools are going to be doing. Those kind of are going to be the replacement concepts for right now. You know that you've got registers in your machine. You know that when you write a program, you know what that program's going to be doing on those registers. That model is going to be gone, and it's what the tools are going to be doing with the program that's going to become important, as opposed to the actual hardware. Okay, so cross-cutting concepts 1. So there are patterns in the world. You know, Johnny throws the ball, right? And those patterns get mapped onto structure in code. So in C, Johnny would be a data structure, ball would be a data structure, and world would be a data structure. And that then gets mapped onto structure in hardware. So those data structures will end up being memory layouts, and the functions, the function throws, will end up changing that state on the hardware. So the humans are the ones doing the world to code mapping, and the tools are the ones doing the code to hardware mapping. Now, it used to be that humans do a lot of that code to hardware mapping, right? You write threads, you know what the hardware is doing, so you write your code exactly because you're going to manipulate that hardware very carefully. That's gone in the parallel world when you write one program that runs on all hardware. You don't know what the hardware is. So that's the reason that the tools become so much more important, and those become the core conceptual model when you're writing your application. You think about what's the tool going to do rather than what's the hardware going to do. Okay. So in the applications, start at the world. Teach use cases, right? We're preparing students for going out and doing stuff. And in the world, this is the way things happen. You get use cases, and then you get a software architecture, and then you get a model. You know, usually it's an object model these days, or it could be data structure model, etc. You've got events in the world, and those map onto functions or functional blocks or methods, etc. in your software. And you have dependencies in the world, right? So Johnny throws ball. If you then have dog fetches ball, well, dog fetches ball depends on Johnny throws ball, right? Because Johnny throws ball changes the state, and the ball is in a new place in the world, right? In the world data structure, that state of the ball has changed. And now the dog fetches ball has to know that new state. So that's where dependency is in the real world between actions that happen. Let's see. So in this course, in this first application course, teach abstract data types just briefly, just to give a flavor of what they are. Algorithms, programming patterns, and a lot of this is still sequential based, but with the dependencies and the processor specifications and software processors in the mix. And then some software architecture, functional blocks, arrow state, and that helps for the concepts of things in the real world and getting those in terms of things that you do in code. Okay, so the architecture track, Yale covered it. It's Yale's course. Compressed a little bit. So memory hierarchy details, class simple, in-order processor. Start at the machine primitives. Top down would start the machine primitives down to the registers, and bottom up would go light switches up to registers. But so the tools track. So this one would be sort of the biggest change so far in teaching. It would enter the freshman course, and it would establish in the freshman's mind what's happening, what's going to happen to my code when I write it. They're going to know what the tools are going to do to the code, rather than what the hardware is going to do to the code. So the tools use the processor specification patterns. And they're going to change those processor specifications to change the state evolution to map better onto the hardware. So teach them about patterns in the evolution of state and how changes in the processor specifications will change that state evolution. Loop interchange that I showed before is a perfect example. And teach the properties of the operations and the patterns. Show how those constrain code transforms, right? So we're talking about tools. Tools change the code. Show what things the tools are allowed to do. Why this loop interchange is allowed, why you can swap the order of adds or change the associativity of adds, and the effect on the state evolution of doing those changes. And do the classic sequential code transforms. Right? Those aren't in freshmen now, and I'm recommending put them in freshmen so that they get this concept of the state evolution that I know when I write my program. The tools are going to change that, and here's what they're doing. Right? You've got this this cache hierarchy. It's going to change this. You've got this big array or this big matrix, and you're doing the sequence of things. Well, it's going to chop up that pattern such that this portion of the pattern fits into this hardware. So you look at the number of addresses, and you look at the data that it fetches, and you add it up. Aha! The data fetched by this sequence in the state evolution fits exactly onto a cache. And then this larger sequence of those fits into the L2 cache, etc. Loop unrolling, it's the same thing. So, and tie those into the semantics of the application. Right? Dependencies in the application, the scheduling constraints, and the transform properties. So, once that first iteration is done, come back to the primitives and fill in more detail, because now we can map those primitives. We can map the state evolution onto hardware because we've had some hardware. We can flesh those out more. So, first, 15 minutes. Okay. So we've got this main memory, and we've got this physical processor, and the physical processor has no state. So all the state is in memory. So to create a software processor from this specification, the compiler is going to translate the scheduling process implied by the language into an implementation of that scheduling process in terms of the physical processor. So that's why you take one keyword and it gets mapped into 3 or 4 instructions. So this scheduling process is going to need some temporary results. Right? If you look down in there, it's got the n compared to 0. Well, it has to remember that temporary result someplace. Right? It also has the n minus 1 before the recursive call. Well, you have to store that temporary n minus 1 result someplace. And you have to do that 1 plus and store that temporary. So creating the software processor is creating all of that temporary state that's hidden inside the language. And the programmer counter is up there because the physical processor in this model has no state. All the state is in memory. So you'll notice that there's a hierarchy here. There is this software processor, and it's got a language, and the scheduling process of that language, that software processor is being animated by the scheduling process of the language. And that scheduling process of the language is a number of instructions. And now those instructions are being animated by the physical processor. And that physical processor is now being animated by a clock, animated by electricity, turtles all the way down. So the physical processor's scheduling process is instruction fetch plus the instruction dispatch. So recursion, once you've got this, recursion is like, duh. You know, you do a recursive call, well, you create another software processor. So, when I've tutored students in computer science, when I show them this model, and we get, you know, they come to me in recursion, and their eyes are like, oh my God. And I walk them through this stuff, and and then when we come back to recursion, they're like, oh, that's so simple, right? You just create another software processor each time you call, and each software processor has its own temporary state, no problem. So now we've had general purpose register in the hardware track, and now we're on the second iteration. So we can talk about the register memory, and I'm including the program counter in the register memory. We can talk about cache and main memory. And here we've created 2 software processors, and the state of them has been copied down into registers. Part of the state has been copied down. So now, when a software processor is being animated by the physical processor, that actually means that the state of that software processor, some of it is down in the registers, and the program counter that's associated with that software processor is the one that the physical processor is currently fetching from. So that gives meaning to, you know, that's program counter. I don't know about anybody else, but the program counter for me, when I first saw it, was weird. It was weird, or something. This should help to, you know, it puts the program counter in the same conceptual model as everything else, as running a function, as doing recursive calls. You know, the program counter, it's the exact same thing. It's the state of the scheduling process of the physical processor. So now we can talk about dependencies in a much better way, and we can show how every dependency means that a series of communication events will take place. So here I haven't shown the details of the access to A inside our software processors, but 2 software processors have been created from the same specification. And they're each being animated by a different physical processor. And so in the evolution of state, at some point, I didn't mark it, I should have, but at some point, because of whatever's inside unspecified, the access A, the physical processor on the left has written to a particular location that's in main memory. So that location's been copied down to the cache, and that's been copied down to the register memory. That physical processor has modified it, it's stored it back into the cache. And now the second physical processor decides it wants to read that same location in main memory. So its instruction that causes a load causes the cache coherency to see, aha, this location also exists over there, and it's been written to. So now I have to go fetch it from main memory, which fetches it from the other location, or it could be on a bus. But this shows that a dependency that's in our original code at some point in the state evolution turns into both physical processors accessing the same location. And that dependency in the code, here's how it maps into a communication event on the hardware. So now we can talk about dependencies at all the different levels. You've got dependencies in the use case. Johnny throws ball's in a different place in the world, so Fido fetches ball. There's a dependency between the throw and the fetch. Throw is the propended, the fetch is the dependent. In an algorithm, there's a modification of a data structure. And so at one point in the algorithm, the data structure is modified. At another point, it's read. And that implies, to teach them, that means that there's a dependency from the modification event to the read event. And then they've got that model, that means that communication is going to happen in hardware after the tools get done mapping the state evolution onto the hardware. In abstract data type, one event interacting with an instance of the abstract data type, right? One interaction causes some state to change inside, and now some other interaction some other interaction with that abstract data type gets a different result because of that previous interaction. That's a dependency in abstract data types. And again, maps onto a communication down in the hardware. In the language, when one statement executes a write and another statement executes a read, and those are either the same variable name that's in the scope, or it's through a pointer that points to the same location, that's a dependency. And in hardware, we just saw that a write of a particular memory location followed by a read is a dependency that causes that communication. So the last thing in this part is dynamic scheduler. This kind of ties things to what's happening right now with multi-threaded programming. And it says why multi-threaded programming is so hard. And this dynamic scheduler that's the scheduling process of the application, right? So current practice is when you write your application, you write creation of threads, you put in a lock, you do a synchronization, and each of these things, right, that thread represents a virtual processor. So each of these things is directly controlling actions in our virtual hardware. And that's the scheduling process, right? It's making decisions about where to create a software process, right? Which thread creates the software processor. That's a decision. Doing communication events, that's a scheduling decision. And so when our scheduling process is written as part of the application code, the tools, it's bad, right? What you want is for the tools to be doing the scheduling. Scheduling is all about hardware. The It's all about picking which processor to put it on, when to put it there, what data to give to each software processor, right? That should all be inside the tools. What should be inside the program is the constraints on scheduling. So here's a slide that talks about that. So the communication latency, right? If you look at the communication happening here, that takes a certain amount of time that depends on the hardware. So that communication latency plus the overhead of deciding to schedule. Right here, the hardware has done the scheduling, so it's not an issue. But if your scheduling process is doing the decision, right? Scheduling processes work with big structures in your software, right? That's one of the big differences between sequential and parallel. Is in parallel, you've got you want to group perhaps multiple of your software, multiple of your processor specifications together as one unit. After your translation, they become one unit. And that unit is used to create a software processor by your application level dynamic scheduler. And so these are big decisions. They take a long time, right? Am I going to put it on my cell SP1 or my cell SP2? Which one gets the work? There's some overhead in that. And if the amount of time, when the data reaches the actual physical processor, if the amount of time to do the full state evolution in that work unit takes longer than the communication time plus the scheduler's think time, then you didn't get any advantage from the parallelism. So one of the key things that tools do in parallelism is they choose the size of the software processors that get scheduled. They either make the decisions of scheduling beforehand in the tools statically, and then insert instructions that do the dynamic part of moving the communication, or they insert a dynamic scheduler for you. And some of the most important transforms are, okay, I'll skip that. So I'm going to have to go over these quickly. In application track 2, now we get to parallel programming patterns because we understand parallelism, we understand what the tools are doing, we understand dependencies, we know about Johnny and the ball, we know that dependencies imply communication, we know that communication is going to get mapped onto the hardware. We know about the structure of processor specifications and that those are the things the tools are looking at. Those are the things that have implied scheduling constraints that allow this dynamic scheduler to put multiple software processors made from the same specification in multiple places and give them different data to do things. We'll point out in the application track that side effects are communications between different software processors. That's what a side effect is. But it doesn't have any semantics about the dependency. It doesn't tell you anything about the scheduling constraints, which is why side effects are bad for parallelism. Architecture track, more of a survey of current parallel hardware, all the different things to give them a flavor. Tools track 2, performance portable parallelism. So the specialization step is the key, right? If you want software that you write once, and then that software runs on the different hardware platforms, you finish the software, it's debugged, it's ready, you ship it, and then there's a second brand new step in the middle, which is called the specialization step. And this is the step where multiple tool chains take that one source, that one shipped, ready to go, it's all finished program, and they translate it into multiple executables. And then you've got some infrastructure so that the end user never knows that there are multiple executables. They've got their machine, they do the install shield process, they get the right one. So let's see. Frameworks and generic patterns. Okay, last slide. So my recommendations are make this a full year course, right? Because all these 3 tracks and the primitives, they intertwine. So you really need to do this iteratively. So it needs to be designed as one whole unit. And once they've got this, then, you know, they can be turned loose on these different specializations. They can go into the hardware track, and they can get the parallel hardware, they can get the out of order, they can get all this great stuff, networks, systems, and tools. I'm actually putting operating systems in the tools class, because the operating system and the tools really should start working together rather than being separate. Concentrate on the, you know, covering the courses, structure and code to state evolution, to hardware, source transforms, tuning, schedulers. And in applications, this is one I really wanted to touch on, which is have a course that teaches project logistics. Okay, I was a hiring manager. I hired people who came out of college and tried to work. And these people, it was a disaster because so much time had to be spent because they did not have the social skills for working on a team. And there's a lot of stress teaching someone who's young and that, you know, they don't get to use their favorite tool, right? There's a process here. It's a company. Everybody has to work together. So there's tools that are pre-decided for a lot of good reasons. Teach them about working with other people, about making decisions together. Those are critical skills that aren't taught. And the way to teach them is give them an open source project as part of the class. And this entire class is all about doing something on an open source project. They learn the development process, they learn tools, they learn the social skills, most importantly, the social skills. And then change to domain-specific track, right? Web is important. That's 1/3 of the jobs. Enterprise, most of the Java actually ends up being enterprise stuff. Big companies want special software just for them, and that's where a lot of the Java people are employed. Desktop, that's where the C++ comes in because it's, you know, you write it once and lots of uses, so they want performance there. Mobile, things are done differently in each of these areas. So the software should be taught according to the area because there are too many things that change. Writing software is not one size fits all. And then the discipline is specific. Abstract data types course, algorithms course, languages course, and theory course. And that's it. That covers it.
Okay, let's move to the, first of all,